Welcome everyone, I'm Norman Wildberger. Today we're going to be introducing arithmetical sequences as an aid to helping our young people practice adding a sequence of digits. So from our point of view, there are really two critical and basic arithmetical operations or techniques that students have to learn at the start of their arithmetical careers. They have to learn how to add a series of digits smoothly and fluidly and correctly. 5 plus 4 plus 7 plus 7 plus 9. 5 plus 4 is 9. Add 7, we get 16. We're wrapping around 10. Plus 7 is 23. Now we're wrapping around 20. 23 plus 9 is 32. We're wrapping around 30. Okay? So this idea of just adding digits and being able to tally up the total as we go is very important. We want to strengthen that. And that's one of the two fundamental techniques. The other one is, of course, multiplying two digits, knowing what 7 times 8 is, or 4 times 9, or anything else like that. Now, from these two sort of foundations, we're going to develop actually some novel techniques for bigger sums and products. So ultimately, we want to move towards being able to sum up some total like this, involving bigger numbers. And of course, doing multiplication with bigger numbers. And we want to develop really good technology for doing that. We're going to be doing this in novel ways, all right? So I'm going to be showing you really new ways to teach young people to do these very important foundational things. But as a preliminary to that, we have to get them fluid with summing digits just individually. And that's what we're aiming for today. Okay, so this aim of trying to understand how to add a series of digits, it's an important skill. Involves, of course, knowing the addition table, understanding the idea of wrapping around 10 or 20 or 30, etc. And it requires lots of practice. Lots and lots of practice. So in today's video, we are going to give an opportunity for establishing this practice through looking at arithmetical sequences, which are, in some sense, kind of simple versions of this, where we're always adding the same digit to whatever we have. So here's an example. 2, 9, 16, 23, 30, 37, 44, 55. This is a rather special kind of sequence. It's an arithmetical sequence because to go from one number to the next, we're always adding the same thing. In this case, 7. So we're starting with the number 2, and then the difference between 2 and the next one is 7. That's how much we have to add to one stage to get to the next stage. So 2 plus 7 is 9. Plus 7 is 16. Plus 7 is 23. Plus 7 is 30. Plus 7 is 37. Plus 7 is 44. Plus 7 is 51. And we could keep going exactly like this. Okay, so we're utilizing both the understanding of how to add 7, but also we're at the same time using the wrapping around idea. So for example, from 37 to 44, we need to know that 7 plus 7 is 14. That's what the addition table tells us. So 37 plus 7, it's like 14. So we have to go from 30 to 40. We're wrapping around 40 to get to 44. Okay? So that's the kind of object that we're going to be looking at today. Now, the most fundamental arithmetical sequence is the sequence of natural numbers themselves. 1, 2, 3, 4, 5, and so on. This is a sequence that starts with 1 and whose difference is always 1. We're just adding 1 to generate the sequence. After that, we have the odd and even numbers. The odd numbers 1, 3, 5, 7, 9, 11, starting with 1, having difference 2. And the even numbers 2, 4, 6, 8, 10, 12, and so on, starting with 2 and still having difference of 2. Now this one here has an alternate description. These are also the multiples of 2. 1 times 2, 2 times 2, 3 times 2, 4 times 2, 5 times 2, 6 times 2. That's another way of thinking about this sequence. So if we keep on proceeding sort of methodically, as we like to do, naturally, step by step, then the next kind of sequences we should be thinking about are the ones with differences of 3. So there are then 3 arithmetical sequences with difference equals 3. The sequence 1, 4, 7, 10, 13, 16, 19, starting with 1. Sequence 2, 5, 8, 11, 14, 17, 20, starting with 2. And the sequence 3, 6, 9, 12, 15, 18, 21, and so on, starting with 3. And these ones here are all the multiples of 3. 1 times 3, 2 times 3, 3 times 3, 4 times 3, 5 times 3, 6 times 3, 7 times 3, and so on. So the multiplication table is appearing here also in this particular arithmetical sequence. Notice also that there's a kind of obvious relation between these sequences. To go from this one to this one, well, we're just adding 1 at each stage. So the initial starting point increases by 1, then all subsequent elements are also going to increase by 1. 5 is 1 more than 4, 8 is 1 more than 7, 11 is 1 more than 10, and so on, because we're always adding 3. So if we're ahead by 1 to start with, and we just keep on adding 3 to both parties, then the second one will always be exactly 1 ahead of the first one. So we generate each of these by just continuing to add 3. Let's have a little closer look at this first sequence that we've just shown you, the one starting with 1 and with difference 3. So the sequences go on, but it's instructive to not just exhibit, half a dozen or a dozen entries, but to actually go further. So 1, 4, 7, 10. We're adding 3 each time. 10 plus 3 is 13. 13 plus 3 is 16, etc. So 19, 22, 25, 28, 31, then 34, 37, 40, 43, 46, 49, 52, 55, 58, 61, 64. Now we're kind of in the same situation we were back then, which is really the same as sort of what we started with, the 4 there. So the 64 goes to 67, just like the 34 went to 37 and the 4 went to 7. And then 70, which is sort of parallel to 40 and 10. 73, parallel to 43 and 13. 76, 79, 82, 85, 88, 91. 94, also parallel to that one. 97. Then 100. Reach another kind of milestone. Now we're into the 3-digit numbers. Okay, well, we can keep going. Then 103, 106, 109, 112, 115, and we could keep going. Now, I don't want you to shy away from writing down a lot of numbers like this. And I want you to encourage your young people to also do this, to have the patience, the diligence, and the carefulness required to set out the entire sequence to quite an extent. So this is very different from just solving a single one-off problem like what is 7 plus 9? It's 16. And then we go off to another problem completely unrelated. What we're doing now is systematically creating a structure step by step. And the structure unfolds and reveals patterns and reveals structure, okay? So there's interesting aspects of this, things to observe that you could talk to your student about. The fact that there's a kind of a repetition. Once we get from here to here, we've added 30, and then after that, things kind of repeat. There's also other interesting things to observe about this kind of pattern once you have enough of them like this. For example, the digits appearing in the ones column. The ones column, the rightmost position in our number. 4, 7, 0, 3, 6, 9, 2, 5, 8, and then back to 1 where we started. What we've done is we've gone through all the possible digits from 1 through 9, actually including 0 also. So all 10 possible digits are occurring as the ones digit in this series. And after here, it repeats. There's a 1 and then a 4 and 7, exactly as we've noted before. So that's the kind of thing that students can observe. It's sort of a pleasant pattern here. It's not ad hoc. There's a bit of structure and something to observe. So there's a good scope here now for activities to give young people. We can get them to create arithmetical sequences with a given start and a given difference. So we can say, start with, say, 5, and let's consider a difference of 8. That means we're going to start with 5 and we're going to keep on adding 8, and we're going to write down all the numbers that we get in exactly the order that we get them. We're going to separate those numbers with commas, so we end up getting a sequence. And the student should write down that sequence. Not just the first 5 or 10, but maybe 10, 20, 30, 40 of them. Every time they make a computation, it's strengthening their understanding. It's reinforcing addition by 8 in this case. Okay, so what do we get? 5. In our heads, 5 plus 8 is 13. 13 plus 8 is 21. Plus 8 is 29. Plus 8 is 37. Okay, I'll stop saying plus 8 because it's plus 8 from then on. So we're at 37, then 45, 53, 61, 69, 77, 85, 93, 101. We're wrapping actually around 100 here. Right? It's like 3 plus 8 is 11, but we've got 90 already. So when we wrap around, the next 10 is 10 tens, or 100. And then 109, 117, and you could go on. And it's really a great exercise to go on like this. Okay? They're learning something. And another thing to note is that if we look at the ones digits that appear, there's a 5, a 3, a 1, a 9, a 7, a 5, a 3, a 1, a 9, a 7, a 5, a 3, a 1, a 9, a 7. There's obvious repetition there, but we're not cycling through all 10 digits now. We're just cycling through 5 of them. 5, 3, 1, 9, and 7, and then it goes back again. It's a small observation, and you could ask a child, why do you think that is? What's different about this situation from the previous? It's a little bit of a subtle question, and maybe it would become more apparent what their explanation is after you've done a few more like this with different differences and different starting points. So there's some experimentation that you can do here with a view of sort of determining what the pattern is, revealing the structure, making some small observations, almost of a scientific nature. So let me make a few more remarks just in that direction about the repetition that's occurring inside an arithmetical sequence if we just look at the pattern of digits in the ones position. You just concentrate on that rightmost digit. We're keeping on adding a certain difference. What happens to the possible values that end up in the ones digits? Well, it depends on the differences. So if you have a difference of 1 or 3 or 7 or 9, in other words, we're starting with arithmetical sequences that start with something and then we're adding either 1 successively or 3 successively or 7s or 9s, then in each of those situations, what happens is that all possible digits can appear and do appear in the ones position. No matter what the start is. It doesn't matter which number we start with, it's always the same phenomena. And that's something that you can observe. Okay, if you do lots of examples, you will see that this is true. On the other hand, if we have differences of 2, 4, 6, or 8, then again you can observe that for any starting point, only 5 digits appear. The same kind of thing that we saw in our example for 8. Okay, so the ones digit repeats, but every 5 instead of every 10. Now these are most of the possibilities. We're not talking about difference of 0 because that doesn't really do anything very interesting. But there's one additional number here, which is what happens with a difference of 5. And then only 2 digits appear in the ones position. Okay, so that's a kind of interesting thing, and if you have students doing this exercise consistently, a lot of them, they will come up with perhaps some observations in these directions. And then you can give some thought to explaining why this is. Of course, there's some number theoretical explanation. It's a little bit subtle and perhaps requires additional concepts, but even young people can get a feeling for it. Okay, so they're getting a feeling about number sense. It has something to do with the relations between these numbers and the base 10 in which our number system is set up. So arithmetical sequences are relatively easy in some sense because we're always adding the same amount at each stage. So there's a repetitive aspect, and it certainly makes it easier to get the hang of what's happening. But we want to move towards being able to readily sum up more random sequences of digits. And for this, it's useful to introduce the idea of a partial sum. Okay, so we're agreeing that we're going to sum from left to right. Left to right. The total at any point is called a partial sum. So we may not have reached the end of the summation that we're trying to add up. We've gone a certain way. The total at that stage is called a partial sum. Okay, so for example, here is a sum that we might have to evaluate. 3 plus 4 plus 4 plus 4. And the partial sums are the numbers that we get at the various stages, starting with our starting number, which is 3. Then 3 plus 4 is 7. 7 plus 4 is 11. And then 11 plus 4 is 15. So 3, 7, 11, these were the sort of stepping stones that we needed to get ultimately to 15. So if we wrote out the arithmetical sequence, these are just the elements in the arithmetical sequence generated in this case by starting with 3 and having a difference of 4 and going up to 15. But here's a more general example where we don't have an arithmetical sequence. Okay, we have a random sum, 5 plus 6 plus 2 plus 8 plus 9 plus 9 plus 3 plus 4. When we want to add that up, we would start with 5. 5 plus 6 is 11. There's 11. Plus 2 is 13. Plus 8 is 21. Plus 9 is 30. Plus 9 is 39. Plus 3 is 42. And plus 4 is 46. So the final total is 46. And these are the partial sums along the way of getting that total. And we can ask young people to generate such partial sums when they're adding something like this up. They can actually write them down. Okay. Ultimately, we want to move toward doing this mentally, but this is a sort of a preliminary stage where we can check their work, make sure they're on the right track, identify where they've made a mistake. Because if they do it in their heads and they get a wrong answer, they've made a mistake somewhere, but where? Okay? So doing it this way, step by step, where you see each partial sum, it's written down, then you can identify where they've made a mistake, and then they can correct that and correct the rest of the calculation. So having honed their skills on the arithmetical sequences, they've done a lot of practice, they've gotten quite smooth at adding 4s repeatedly and adding 7s repeatedly and so on. We can now practice writing out partial sums for more arbitrary sums of digits, which ultimately is what we're going to be needing in actual practice. So for example, we might want to find this sum, 4 plus 9 plus 8 plus 3 plus 1 plus 7 plus 7 plus 8. And we can write out a solution this way, actually write out all these numbers separated by commas. These are the partial sums involved in this big summation. Starting with 4, that's our starting point. Then 4 plus 9 is 13, plus 8 is 21, plus 3 is 24, plus 1 is 25, plus 7 is 32, plus 7 is 39, finally plus 8 is 47. So they have to understand the addition table pretty well to be able to do that smoothly. They have to understand the idea of wrapping around 10 and 20 and 30 and so on. So great practice, okay? So you just give them a sum like this, ask them to write out all the partial sums. And this is great preparation for ultimately doing it mentally. Once they have expertise and competence, then we can be confident that they can do this mentally in their heads. They can just add them up in their heads and they will get 47 because they've practiced this over and over in a variety of different contexts. So important. So important that they actually do this. They spend hours and hours, one way or the other, practicing this essential skill. But of course, we don't want things to become too repetitive or too boring because then young people will lose interest. So we have to spice things up a little bit. And one way of doing that in this context is to throw in some what's the next term puzzles. Okay. And this is very popular in sort of IQ tests where you're given a sequence of numbers and you're asked what is the next term or what are the next couple of terms. So here, for example, 3, 12, 21, 30, 39, 48, 57. What's the next term? What's the next term after that? Well, hopefully, if they've done a lot of examples along the lines of this video, they will recognize that to go from here to here, we're adding 9. And that's also adding 9. And that's also adding 9. And so is that, and so is that, and so is that. And so the pattern is clear. This is an arithmetical sequence. And the next ones are going to be obtained by adding 9. So 9 plus 57 will be 66. And 9 plus 66 will be 75. Here's another example, but this one not necessarily starting with a small number. Okay? These arithmetical sequences can actually start anywhere. So here we're starting at 12. And then we're going 19, that's adding 7. And then 26, that's adding 7 again. And that's adding 7 again, adding 7 again, adding 7 again. And so you'll be able to predict what the next two are. So this idea of getting young people to think, okay, how much do we have to add to where we are now to get to the next one? Right? What is the difference between where we are and where we're going to be? Okay? And so keeping track of those successive additions that are required. Here's another example, maybe a little bit outside of what we've been talking about because it's an arithmetical sequence, but with a bigger difference. So here we have 7, and then 18, 29, 40, 51, 62. What do we have to add to 7 to get 18? Well, you have to add 1 to 7 to get 8, but there's also a 10 here, so we have to add 10 plus 1, that's 11. That's how much we're adding to 7 to get to 18. And that's actually also what we require to get there. We're adding 11 to 18. 11 to 29 is 40. 11 added on to 40 is 51, and so on. So we're kind of stretching the boundaries of what they have some experience with, but they can probably end up doing this. Here's another example. 5, 11, 15, 21, 25, 31. I guess the pattern's kind of clear because we're kind of alternating with 5s and 1s, right? That's one way of looking at it. 5, 1, 5, 1, 5, 1 in the 1s position. And otherwise, we're kind of going up in stages with the 10s position. But what about in terms of differences? Here there's a difference of 6. We have to add 6 to 5 to get 11. But to get to 15 from 11, we have to add 4. So we've added 6 here, and then we've added 4 here. And what about here? We've added 6, added 4, added 6. Okay, so that's a little bit different, but there's a pattern there. Right? We can identify what the pattern is. Add 6, then add 4, then add 6, then add 4, then add 6. So the next one should be add 4, which would be 35. And then the next one after that would be add 6, which would be 41. And what about this one? 2, 6, 15, 19, 28, 32, 41. We're adding 4. We're adding 9. We're adding 4. We're adding 9. We're adding 4. We're adding 9. we can get the pattern. We can predict what's going to happen afterwards. And there's lots of variants like this, and they can get a little bit trickier, of course, but still this is a great little exercise to throw in there while we're doing arithmetical sequences, just to give them some experience with things which are a little bit more general, a little bit trickier, maybe requiring some novel thinking. Okay, so that's great. That's a very important tool. And now in our next video, we want to go further, okay? But what we're going to do is to motivate our sort of next thinking in terms of addition, we're going to actually shift gears to talking about money. Okay? Talking about money is a great way of introducing another angle on addition because it has natural practical applications. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.